domain. Okay, the author, please.
Yes, I currently joined the meeting, so I will be giving the presentation. You guys can hear my voice clearly, right?
Yes, carry on, please.
Okay, sure. Wait a second, I'll just share the screen for my PowerPoint.
Okay, thank you.
So I'll be giving my presentation in a few seconds, just to get a sip of my water. Perfect. You guys can see my video of myself, right? That should be working. Sure, I'll be giving my presentation. So welcome, ladies and gentlemen. My name is Jaechul Roh. You can call me Harry, and I'm currently a final year student, undergraduate student in Hong Kong University of Science and Technology, majoring in computer engineering. Today, I'll be giving a presentation on the paper which I worked on with Professor Minhao Cheng and Dr. Yajun Fang, named MSDT, short for Mass Language Model Scoring Defense in Text Domain. Now, let's get started. Now, the presentation is separated into four main parts: the background information that explains the concept of versatile attack, introduction to backdoor attacks, slash defense in natural language processing, followed by a section where we introduce our novel proposed algorithm, MSDT, which aids to defend against NLP backdoor attacks. We then demonstrate some empirical results in section 4, depending on different conditions. And we finally conclude our presentation by explaining the significance of our research and a summary of our novel findings. Now, before getting into the main sections, let's go over some major concepts that needs to be understood. First of all, a versatile attack is a technique to maximize the misclassification of a clean model. To do so, we need to create an adversarial example where we normally add a small perturbation to the original input, where the difference between the clean input from the original input image needs to be imperceptible. The adversarial example will intentionally lead to the model to misclassify with a high confidence level, where the image is predicted as dog with a 99% confidence, while it is supposed to be classified as the Alps. Now, various algorithms have been introduced to create an adversarial example. One of the groundbreaking ideas came from the algorithm called fast gradient sign method, also known as FGSM, proposed by a researcher named Ian Goodfellow. The method proceeds in the following manner. The adversarial example is obtained by first calculating the sign of the gradient of the loss between the input and the output. We then multiply by the perturbation rate, denoted as epsilon, and add to the pixels with an L infinity constraint. After that, calculating the loss between the original input with the created adversarial example will allow the image to leave the adversarial boundary, eventually leading to misclassification. Now, another branch of adversarial attack or robust machine learning is a method called backdoor attack. The concept was first introduced by Cheng in his paper named Batnets, where it identifies the vulnerabilities in the machine learning model supply chain. As the diagram shows, by adding a specific backdoor trigger to the image, such as small bomb, flower, or even a single or pattern-based pixels, it activates the backdoor classifier within specific neurons. The network in the middle is also used by an attacker to recognize the backdoor trigger in the user-specific network, but he or she must not change the architecture itself. Now, although such a method demonstrated a fairly high attack success rate in image domain, it has still been a challenging task in the field of natural language processing. This is because since images consist of continuous characteristics, adding a minimal noise to the pixels will still make the adversarial example imperceptible. On the other hand, since the text domain is discrete characteristics, the neural network will easily distinguish the difference between the poison text from the original input. Now, recently, quite a number of papers have been published with high attack success rates in NLP with the help of backdoor attacks. Hidden killer is a method to syntactically change the input text, which means that the sentence will be changed to an entirely different sentence, but with the same meaning. Another method is to replace the keywords within the text to a synonym, which also confuses the language models to process classification. There are also other attack methods, such as paraphrasing the input sentence or summarizing the entire paragraph. We will now take a look at how we defend against such methods. Now, in the next two slides, I will kind of introduce the state-of-the-art backdoor defense algorithm in text domain named Onion, short for backdoor defense and outlier word detection. In fact, compared to the amount of research conducted in backdoor attack NLP, there are only a handful of papers that introduce the defensive algorithm. Onion experimented with a poison BiLSTM and BERT model using 3 different attack methods, BATNet, ripples, and incent. For BATNet, it injects low, middle, or high frequency words randomly as triggers depending on the dataset. Ripples adjust the embeddings of the trigger words, and finally, incent injects a fixed sentence as a backdoor trigger. Now, in order to detect the trigger words, Onion first calculates the perplexity of the whole sentence. Perplexity is a valuation metric for NLP language models that measures the fluency of the output text. Then it computes another perplexity by removing each token from the sentence. Getting the difference between those two scores will be the suspicion word score, also denoted as FI. We may notice that the higher the FI value implies that the I token is the outlier word, since the sentence will have a higher perplexity if it is not fluent enough. Now, here are some issues. Onion actually achieved some fairly good results in specific data sets. However, we spotted two main issues that reside within the algorithm. First problem is that Onion uses a perplexity score based on the GPT-2 language model, while the victim models are by LSTM and BERT, which do not match semantically and contextually. Another issue revealed in the paper is the amount of normal words removed. 57% of non-trigger words are removed from the poison dataset and 63% from the clean dataset. This could also impact the classification ability of the language models. Now, the final concept that we need to take a look at, which is also the most crucial part, is the masked language model scoring. It calculates a sentence score by summing up all the log probabilities of the copies of a sentence with each token masked out, which gives us a pseudo-log likelihood score associated with pseudo perplexities. Now, we will now introduce our proposed algorithm in the next following slides. Now, MSDT, short for Masked Language Model Scoring Backdoor Defense in Text Domain, is our novel improved backdoor defense algorithm that outperforms the Onion in specific datasets. As a general overview, we first calculate the masked language model scores and filter out the trigger based on the threshold. Then we re-evaluate on the poison BERT based on the filter sample and check the classification ability. Now, let's take a deeper look into how our algorithm works. We will have a list of sentences and create an empty list of scores. For every sentence, we split the sentence into tokens and remove each token one by one. We calculate the MLM score for each token and save it into the score list. Now, the second part of our algorithm relates to filtration. So for every threshold and every score, we calculate the difference between the scores and the score average, which we obtained in the beginning of this part 2 algorithm. After that, we remove the specific I token with the difference bigger than the threshold value. According to our experiment, the threshold value in the boundary of 5 to 22 demonstrated the best detection ability. Now, here's a direct example of a single input sentence and how we process our algorithm. The sentence will be split into different tokens where MB is the backdoor trigger injected by the attacker. If we calculate the MLM score for each token removed, you may notice that removing MB will give us the lowest MLM score, which suggests the sentence becomes more grammatically and semantically clear rather than being perplexed. However, this is not enough. In order to not remove any clean normal words, we will calculate the absolute value of the difference between the score and the score average, which implies that such a word is an anomaly. As we set our threshold value as 14, the token removed will be the trigger word, and if we process the same algorithm, the clean data set, we may see that no words or no normal words are removed. Now let's talk about empirical results that we obtained during our investigation. We used 3 separate data sets to test our algorithm: SSC2, DBpedia, and AG News. SSC2 is a data set for binary classification tasks in sentiment analysis. The model will classify either 1 being positive and 0 being negative sentiment. DBpedia is a multi-label dataset that consists of 9, 70, and 219 classes. For simplicity, we only utilize the dataset with 9 labels. AG News is also a multi-class classification dataset with 4 labels: world, sport, business, and science. The selection of the datasets was highly based on our multi-label characteristics, which we believe that the classification accuracy could react more sensitively compared to the binary classification tasks. Now, for simplicity and lucid comparison, we have used BERT as our victim model and BAT-NL as our attack algorithm. BAT-NL randomly inserts rare word as triggers to poison the input text. The triggers were chosen based on the least frequent tokens from each dataset, although Onion also experimented with middle or high frequency word as well. The trigger rate was set to around 5% since it was enough to poison the BERT model. Now, to accurately measure the effectiveness of MSDT, as well as to make a good comparison, we have used the same evaluation metric proposed by Onion, which are ASR, CACC, delta ASR, and delta CACC. ASR and CACC represents the attack success rate and clean accuracy on the clean dataset after removal. delta denotes the change in those values after employing MSDT to the text. For delta ASR, it is definitely higher the better, since it means that the triggers are successful removed. For delta CACC, it will be lower the better, because it means that the less normal words are removed. Now for ASR, the poison bird was able to achieve 100% in all three datasets. After applying MSDT, the tax success rate decreased by 78% for AG News and 84% for DVpedia, which performs significantly better than Onion, with only 47 and 42% decrease in those by using Onion. Although Onion performed better on SST2, we may notice that there was not much difference in terms of their decrement compared to MSDT. This clearly suggests that the model reacted more sensitively when MSDT was able to selectively remove the trigger words within the poison text of the multi-label datasets. Now, for clean accuracy, in fact, Onion showed a slightly better defensive ability in AG News DVpedia. However, especially for DVpedia, the distinction between their performance does not vary that much. At the same time, MSDT actually performed way better in SST2 datasets. Now, if we take a look at Table 3 and Table 4, although MSDT and Onion both remove the existing triggers that reside within the sentence, Onion tends to remove more normal words than MSDT. Now, our method was successful in terms of selectively extracting the trigger words while not removing any clean normal words from both the poison and the clean dataset. Table 3 and Table 4 further illustrates how MSDT was better in processing the given defensive task. Now, here's a summary as well as an evaluation of the experiment that we have conducted. The significance of our research can be illustrated in three main factors. To begin with, there's a lack of research in textual defense, where the field focuses more on the successful backdoor attacks in NLP. The defense algorithms proposed previously were BKI and Onion, which are novel method MSDT outperforms in specific settings. In addition, some backdoor attacks have proved that the publicly released language models could be highly vulnerable, which also poses a significance of the research in this field of area. Finally, typos and grammatically incorrect sentences could always be inputted to pre-trained language models. Such errors can react as triggers and easily lead to malfunctioning of deep neural networks. To summarize our proposed method, it is a novel improved textual backdoor defense algorithm that performs the state-of-the-art Onion in specific datasets. Since it resolves a third-party perplexity issue by utilizing the mass language model scoring, it was able to perform significantly better than Onion, especially in the multi-label classification datasets. As for further studies, we would like to propose for future researchers to investigate different types of textual backdoor defense methods. Both Onion and MSDT are based on detecting backdoor triggers within the input text. However, attacks such as Hidden Killer and Text Fooler use injecting syntactic keywords and replacing specific tokens with synonyms to poison the language models. To defend against such backdoor attacks, research needs to be conducted in implementing a defense method that understands the grammatical structure of the text and classifying whether the input sentence is syntactically modified or not. Such algorithms will aid the users to feel relieved and be trustworthy of the publicly released pre-trained language models and be satisfied by their robustness after processing backdoor textual defense. Now, thank you here are some references that I have used for my presentation, and thank you very much.
Okay, thank you. It's very interesting. And the results, okay, are quite impressive. Any other questions? Any questions, please? Does anyone have any questions? Okay, then I have one question. So because your algorithm, okay, is based on the scoring method.
Yes.
Is that right? Okay. So, but yeah. I'm not quite sure how did you score each word or each example in your algorithm?
Oh, you mean technically, like in code-wise?
Yeah. Yeah.
Oh, so there's a package that is released from the MLM, the mass language model scoring, from this paper. They released on GitHub, so that we can use in open source, where we just input the sentence tokens, like a list of sentences, into the MLM score, which can actually use in the PyTorch model. And we actually use the poison bird model as the baseline architecture, and then if we input the sentence, the scores will be outputted in this specific format. So these scores are outputted from that open source package that they released on the GitHub. So that's how we got the scores. Basically.
Okay, is this the only scoring method? Okay, do you have some other method to score, for example, each word?
So normally, in order to see the fluency of the sentence, the best method is like previously used method was here, where they use the GPT-2 GPT-2 perplexity. But right now, as I mentioned, because we're trying to poison like BERT or BI-LSTM, which is not highly related to GPT-2. So we believe that other scoring methods are not existing currently, because scoring the sentence based on a mass language model is actually not really easy, and not that easy. So right now, this was the only paper that we found in order to score the fluency of the sentence. So I think like in the future, if there's a lot of more scoring metric where we can actually score the sentences, it will be better. But right now at this stage, I think this was the best choice that we have to choose. Yeah.
Okay, thank you. So maybe I think the scoring method, will influence the final results of any algorithm.
Sorry. What was the question?
Okay. I think the scoring method, different scoring method would affect the final results of your model.
Yes, absolutely. It's gonna impact the entire algorithm, because the stage itself, the algorithm itself could be simple, but the scoring is like the major factor. So we try to choose the scoring factor more carefully, so that in order to have a better defense ability for the model itself. So yeah.
Okay.
Good. Thank you for your point as well.
Okay.
No problem. Thank you.
Yeah. Thank you. Any other questions, please? Okay. Any other audience has any other questions? Okay, if there's no more question, and we have to end your presentation. Thank you very much.
Thank you. Thank
for
you
your
so much.
very interesting presentation. So
Absolutely.
now,
thank you.
Okay, we have to invite the next one. The next one is the fifth one.